All right, so here's an example of a problem that we might have for learning objective 2, which basically focuses on standing waves. So this is the question. When one of the strings on your musical instrument is vibrated in its third overtone, which also corresponds to the fourth harmonic, it produces a sound wave of wavelength 0.782 meters, which corresponds to the note A. So the idea is when the string is vibrating, it's producing the sound wave, which is going to travel at a different speed. That's something that we kind of are assuming. The frequency of the standing wave is going to be the same as the frequency of the sound wave because that's how we hear it. That's the pitch. So the first thing we're asked about is to find the frequency of the sound wave. So we're just using the simple relationship between velocity, frequency, wavelength. So we want to find the frequency. So we'll take the velocity over the wavelength. So it's 344 over 0.782. And that turns out to be 439.9 hertz, which we're going to just call 440 hertz, just to be simple. Part B is drawing the standing wave on the string. I'm going to just draw up to the one that we need, just so we see them. So this is the fundamental mode, which is also the first harmonic. That's when you don't have any nodes in the middle. It's just one big antinode in the middle, and it's fixed, of course, at the ends. And so then we just kind of go from there. We just add pieces, in a way, is one way to think about it. We put a node in the middle, and then we have two antinodes here, node in the middle. So this becomes the first overtone, and it's the second harmonic. I'm actually kind of writing these to help you sort of solidify this information. I'm not a very good drawer. This is the second overtone. I don't know why it kind of looks like a monster to me. Maybe because I put those little dots in the first overtone. It looks like eyes. The second overtone has the three antinodes. Again, we're just adding the antinodes to get to the next standing wave. This would be the third harmonic. And finally, we're going to get to the one we're looking for, which is, I drew it wrong. It has two full wavelengths. It's got four antinodes. So this is the third overtone. That was the one we were looking for. It's the fourth harmonic. So that's part B. In part C, we're trying to figure out what the wavelength is. So here, I know from here to here is L, and this contains two wavelengths. So the wavelength is just L over 2 for this standing wave, which is 45 centimeters, because the length of my string, I was told, was 90 centimeters. The speed of the wave, so now we have, for the wave on the string, we have the frequency and the wavelength. The frequency is still the 440 hertz, but we have a different wavelength when it's on the string. And so we get a speed of 198 meters per second. And then finally, we're asked a question like, if the string has a mass of 10.5 grams, what's the tension? That's looking at this relationship between tension and mass distribution. Mu is mass per unit length. So I'm going to rearrange this to solve for tension. It would be V squared times mu. The mu, remember, is the mass per unit length. So I have everything I can plug in. 198 is the speed. The mass is 10.5 grams, so I have to multiply that 10 to the minus third to put it into kilograms. I might have said that backwards. And then the length is 90 centimeters or 0.9 meters. This gives me the tension in the string, which is 457 newtons. Seems kind of big, but I kind of made some stuff up here, so maybe that's why. So this is a question, some of the things you might be asked. There is some variation to what could be asked on this LO. We can't see everything, but if you have the basic ideas, you can figure it out.